Okay, so today we're going to be working on chapter 4.7, which is more equations and inequalities. Most of this chapter, we're going to be looking at how to solve rational equations, as well as polynomial and rational inequalities. It's pretty similar to quadratic inequalities, but there are a couple of weird things that we're going to have to do. But we're going to start with solving rational equations. So rational equations such as 4x over x minus 1 equals 6 can be solved in multiple different ways, including symbolically, graphically, and numerically. Any rational equation in which a over b equals c over d, where neither b nor d is equal to 0, is equivalent to ad equals bc. So remember, b can't equal 0. If b equals 0, then a over b is undefined. D can't equal 0, otherwise c over d would be undefined. This idea right here, I'll just talk about in a second, is known as cross multiplication. So basically all we did, to get from here to here, from a over b equals c over d to ad equals bc, is if you multiply both sides by d and you multiply both sides by b, right, the d's will cancel on this side, the b's will cancel on this side, you're left with ad equals cb. Basically, it's just to get everything all on one level, so it's a little bit easier to solve. There is one key thing that you need to remember, though, is any point in which b or d in the original equation would have been 0 doesn't work as a solution. So we'll see an example of this in a little bit. Also, one thing to remember is that whole numbers, so like in this case, we have the 6, can be written or can be thought of as a ratio of n over 1. So 6 is equal to 6 over 1. 2 would be equal to 2 over 1. 28 would be equal to 28 over 1. Basic, just knowing that numbers work like that as fractions. That also gives us something to cross multiply with, which is why I bring it up. But so we're going to try to solve the equation we just looked at, 4x over x minus 1 equals 6 symbolically. We want to start by writing it in the form of a over b equals c over d, and then we use cross multiplication. So basically we want to start by translating that 6 into a ratio, 6 over 1. And then we're going to cross multiply, so times 1 times 1 times x minus 1 times x minus 1. So 1's cancel on this side, x minus 1's cancel on this side. We get 4x equals, and we need to distribute the 6, so 6x minus 6. And then from here, this should be a pretty easy solve. Subtract 4x, 0 equals 2x minus 6, add 6. 6 equals 2x, divide by 2, and x equals 3. That one's pretty simple. Once you get to this point here, hopefully this equation is really easy for you to solve. It's basic algebra at that point. So solving this function or this rational equation graphically and numerically is actually pretty similar to stuff you've done before. You're going to graph each side of the equation in your graphing calculator. So in this case, you graph y1 equals 4x over x minus 1. Basically just y1 equals this side, y2 equals this side. When you do this in your graphing calculator, it's going to give you something that looks, as I recall, something like this. So there's the y equals 6, and then 4x over x minus 1 looks something like that. I don't know if that's exactly what it's supposed to look like, but it's somewhere close to that. And what this does is intersects at the point where x equals 3. It'll be 3 comma 6, because obviously y equals 6, but whatever. This one is super easy to do in a graphing calculator. Some of the other ones won't be quite as simple, but basically you're just looking at any points where they intersect, and then the x value is going to be the one that's the solution. So x equals 3. Yeah, that's what that just said right there. But to solve it numerically, you just move to the table value view. So I think you just hit table in your graphing calculator, and it'll show you a bunch of values that look like, x, y1, y2, and 0, 1, 2, 3. I don't actually know. This would be undefined. This would be 6. These are all going to be 6, actually. Think about it. And then this one, I don't really know. This would be 0, right? 0 over negative 1. 2 would be 8 over 1, so 8. Then 3 would give you 6. So you look for where these are equivalent, which is right here. So this would be our answer, x equals 3. Yeah, that's just plugging stuff into a graphing calculator, so I'm not going to talk about it too terribly much. I don't really care if you can do that part. That's not that difficult or mathy anyway. Multiplying by common denominators. So this is kind of important. With rational equations, it's a lot of the time you have fractions that are really annoying to deal with. You have denominators that look like this, and that's just kind of a pain. So a lot of times what you want to do is use a common denominator to simplify your equation. And we can multiply everything by a common denominator right at the beginning to simplify the whole thing. So for instance, in this one, we have 6 over x squared minus 5 over x equals 1. If we multiply this entire equation by x squared right off the bat, it's going to make everything a lot easier. So 6 over x squared times x squared, the x squareds are going to cancel. 5 over x squared, or 5 over x times x squared, we're going to be left with 5x, and then 1 times x squared will equal x squared. So in this case, we get 6 minus 5x equals x squared. That's a lot easier to solve than this gross equation right here. Just remember that if we get a solution of 0, 0 squared is 0, so this would be undefined. 0 obviously is 0, so this one would be undefined as well. So x cannot equal 0, no matter what this solves out to be. Luckily, when we solve this, we'll see that it doesn't. So to solve this, we just want to turn this into a quadratic equation. We're going to add 5x. We're going to subtract 6. 5x minus 6. And that gives us x squared plus 5x minus 6 equals 0. I just flipped the sides, doesn't really matter. And then we just want to factor this. This factors to x plus 6 and x minus 1, I think. X squared, 6x minus x, that's plus 5x minus 6. Okay, so this is what this factors to. That means that x equals negative 6, comma 1. Now, whenever you finish solving an equation like this, you always need to go back and check your solutions to make sure they don't give you some kind of undefined number in the original equation. So in this case, if we plug in negative 6 down here, that's going to be 36. That's perfectly fine. It's a real number. 5 over negative 6, that's also a real number. So no matter which value we plug in, and then 1, we'd have 1 squared, which is 1. We'd have 1 over here. Both of those are perfectly fine. No undefined values there, so both of these answers work. You do need to check that on every single one because we're going to run into situations in which the x values will give us an undefined answer. This one here is a little bit more complex, obviously, by the title, more complex common denominators. This one, in order to find the common denominator quickly, you have to recognize this right here is a special type of quadratic. Specifically, this is the difference between two squares. So if you'll remember the difference between two squares from Algebra 2, which you might not, if you have x squared minus some number that is a perfect square, in this case, this is 7 squared, right? 49 is 7 squared. This factors to x plus 7 times x minus 7. Right, x squared minus 4. 4 is equal to 2 squared. So that would factor to x plus 2, x minus 2. Basically, all this is saying is that these are really easy to factor. Now, if we factor this one, what we have is 1 over x plus 3 plus 1 over x minus 3 equals 6 over, and then this factored out is x plus 3 times x minus 3. Which, as you'll notice, is these two values multiplied. So this right here is actually a common denominator for all three of these. So what we're going to do is we're going to multiply everything in this equation by x plus 3 times x minus 3. Now, when we do that, what we'll get, start with this term right here. It's x plus 3 times x minus 3 over x plus 3. Plus x plus 3, x minus 3 over x minus 3, and then equals 6 times x plus 3, x minus 3 over x squared minus 9. Now, I just got through explaining that these are the same thing. This is equal to that, so these cancel. That part's easy. On this side, we have the x minus 3 cancels. And on this side, we have the x plus 3 cancels. That leaves us with x minus 3 plus x plus 3, there's too many crosses here, equals 6. We have a minus 3, we have a plus 3, those cancel out. That leaves us with 2x equals 6. And then we divide these out and we get x equals 3. Now we need to check, make sure that our answer actually works. So if we plug in 3 here, we get 1 over 3 plus 3, that's 1 over 6. That's perfectly fine. If we plug it in here, we get 1 over 3 minus 3. 3 minus 3 is 0. So this one would be undefined if we plug in x minus 3. That means that this solution doesn't actually work. So this has no real solutions. Now, interestingly, because x minus 3 is a factor of x squared minus 3, if we plug in 3 here, that one won't work either. X squared minus 9x, if x is 3, that's 3 squared, which is 9, and 9 minus 9 is 0. So once again, we'd have an undefined factor here. So in this case, there are no real solutions to this problem. Now, let's change gears just a little bit. We're going to start talking about inequalities. We just finished up equations. You should already know how to solve polynomial equations. That part we've covered pretty much this whole chapter. Inequalities really doesn't change a whole lot. It's almost the exact same as quadratic inequalities, but now you can have more zeros. So you'll have more intervals to check, and it's a little bit more of a pain. But solving polynomial inequalities is very similar to solving quadratic inequalities, like I just said, in that we always want to start by changing our inequality to an equation and solve. Graphical solutions can still be found by setting the equation equal to 0, graphing it, and looking where the inequality is actually true. So this part you guys should know how to do. I'm not going to talk about it too much. If you have questions about it, we can talk about it in class, but I'm not going to test you on your graphing skills anyway. That's not really important right now. Symbolically, we will still end up with a set of intervals based on the zeros of the function. We will need to test each interval to see which ones work and which don't. So let's start by looking at this equation right here. We've got x cubed is greater than 2x squared. First things first, make it an equation, and then set that equation equal to 0. X cubed minus 2x squared equals 0. Okay, then we want to solve this. Now, this one's pretty easy to do. Both of these have an x squared in them, so we're going to factor out x squared. If we do that, we get x minus 2, and then we just need to solve these. So x squared equals 0, x minus 2 equals 0, x equals 0, x equals 2. That one's pretty easy. Now that we've solved these, we have 3 different intervals. We have negative infinity to 0, because that's the smaller value. We have 0 to 2, that's our in-between, and then we have 2 to infinity. Okay, then we want to pick test values for each interval. The book suggests making a table of these. I don't really see how that's any easier. If it is easier for you to make a table, go for it. Personally, I don't think that. I think that honestly just adds extra steps, so I'm not going to bother with it. Now remember, we want to plug these into our original inequality. Don't go to this one here, don't go to this one here. Plugging these into the original one. If we try to do the other way, we might get confused as to where the symbols are. Always plug it into your original inequality. So in this case, negative 1 cubed equals negative 1. Negative 1 squared times 2 equals 2. Negative 1 squared is 1. 1 times 2 is 2. Negative 1 greater than 2. This is not true, so this one does not work. Now we can pick 1. 1 cubed is 1. 1 squared is 1 times 2 is 2. So we get 1 greater than 2. This is also not true, so this one also doesn't work. Then we try 3. 3 cubed is 27. 3 squared is 9 times 2 is 18. 27 greater than 18. This one is true. So our answer is x equals the interval 2 to infinity, or x is greater than 2. You can either way. This one, there's also like a trick. If you think about x cubed is x times x times x, and then you have 2 times x on this side. You just need to figure out a value where basically, because you can divide both of these by x squared, these cancel, you just have x needs to be greater than 2. That one's kind of a cheat trick, but whatever. Next up, we have solving rational inequalities. So these are a little bit tougher than solving polynomials. They give us kind of a weird set. So rather than simply having zeros, rational inequalities also have x values which are undefined, right? Anytime the denominator of rational inequality or a rational function equals 0, your value is undefined, you get a vertical asymptote. Those won't work. So when we're solving rational inequalities, we can still do it graphically the same exact way. That one's pretty easy. Graph it, see which x values, and give you a y value that fits the inequality. Not too bad on that one. But solving rational inequalities symbolically requires 4 steps. Now, I would strongly recommend writing these 4 steps down. They're going to be relatively important, and knowing how to do this symbolically is the part that I actually care about, not so much the graphically way. Step 1 is, if necessary, write the inequality in the form of p of x over q of x is greater than 0. This greater than symbol can be a less than, it can be greater than or equal to, it can be less than or equal to, it doesn't actually matter. Point is, get it so that you've got one function over one function and then a 0 on the right side. Okay, that's step 1. Let me clear that out, sorry. Step 2, solve for p of x equals 0 and q of x equals 0. P of x is our numerator, q of x is our denominator. Anytime q of x equals 0, we have a undefined quality or quantity for our function. That's not good. And anytime p of x is 0, then we have a 0 on the equation. Use the solutions above to create disjoint intervals. On these intervals, p of x over q of x will always either be positive or negative. So for instance, you'll get a bunch of intervals, let's say like 2 to 3, 3 to 7, 7 to infinity, and negative infinity to 2, right? You'll get a whole bunch of intervals. You want to pick a test point for each one, and then you'll plug those in and solve them. So test values from each interval to determine whether they satisfy the inequality in step 1. This is the one time where you're allowed to use an inequality that isn't your original one. I would recommend using the original one, but often this one's going to be a lot easier to actually test your points in. Just make sure that you know which values cannot be equal to or cannot be solutions to your inequality. Because again, if you run into, all of these, if you get to a point where you think you're including one and it happens to be a 0 in the denominator, that means it's an undefined value, so it can't be included, even if it's an equal to symbol. So solving rational inequalities. This first one, we've got 2 minus x over 2x is greater than 0. Now, luckily, step 1's already done for us. It's written in the correct form, so we can skip that one. Then what we want to do is we want to solve for the p of x, that's our numerator, and we want to solve for our q of x, which is our denominator, are equal to 0. So let's do this. I'm going to break them up just for fun. It doesn't actually matter in this case, but might as well. Numerator, denominator. So 2 minus x equals 0, 2x equals 0. This one's simple, x equals 0. This one's also simple, x equals 2. So there we go. We got our 2 points. No other solutions to this one. Keeping it fairly simple, which means our intervals are negative infinity, comma 0. Actually, wow, these are the same intervals as before. 0 to 2, and 2 to positive infinity. I'm going to pick test values. I'll do the same ones, -1, 1, and 3. 1 is in between these two. 1 is less than 0, but greater than negative infinity. 3 is greater than 2, but less than infinity. Easy enough. Plug each of these into the original equation. So 2 minus -1, that's 3. 2 times -1 is -2. This is -3/2 greater than 0. That's not true. This one does not work. If we plug in 1, we get 2 minus 1. That's 1 over 2. 2 times 1, which is 2. 1/2 greater than 0. This one does work. And then we plug in 3. 2 minus 3 is -1 over 2 times 3 is 6. -1/6 is not greater than 0. So this one does not work, which means our solution is x equals the interval from 0 to 2. Okay. This one is a little bit trickier. We have 1 over x is less than or equal to 2 over x plus 1. Now, in order to do this, first we want to set these on the same side. We're going to do that by subtracting this whole gross thing from each side. 2 over x plus 1. So we get 1 over x minus 2 over x plus 1. is less than or equal to 0. We can just change this to an equals now because it's not going to make much of a difference. We're going to plug it back into our original equation so that we can test our undefined quantities at the same time. So here we have, let me erase this, hold on, sorry. Okay, 1 over x minus 2 over x plus 1 equals 0. Now, we want to get rid of these. These are awful to have in the bottom, so we're going to use a common denominator. In this case, we're going to use x times x plus 1. So we multiply this by x times x plus 1. X's cancel. X plus 1 minus, and this time we're going to use x plus 1. The x plus 1's cancel, so we have 2x equals 0. X plus 1 minus 2x, that simplifies to 1 minus x. Right? We have a positive x, we have negative 2x, that's negative x equals 0. So in this case, we get, since we didn't have a denominator when we actually solve these out, we get that x equals 1 as our solution. Now we can also check the points where our denominators are equal to zeros or are undefined. In this one, it's going to be x equals 0. Oops, x equals 0 and x equals negative 1. So we should have intervals from negative infinity to negative 1. We should have an interval from negative 1 to 0, an interval from 0 to 1, and an interval from 1 to positive infinity. Now, this one is a whole bunch of different intervals. They're kind of a pain to check. This one's easy, negative 2. This one's easy, 2. These ones are a little bit more annoying. We can do like negative 1/2 and 1/2. It's probably going to be the easiest thing to test. Usually it's helpful if your intervals are bigger than just a like one number difference, because then you can use a whole number. In this case, we don't have that luxury, but luckily nothing's squared or anything like that. So let's start by plugging in negative 2. We would have 1 over negative 2 less than or equal to 2 over negative 2 plus 1, that's negative 1. So in this case, we have negative 1/2 less than or equal to negative 2. That is untrue. You'll notice that, or negative 2 is smaller than negative 1/2. It's further to the left, so this one does not work. Then we'll use negative 1/2. So you have 1 over negative 1/2. This is equal to negative 2. Right, you're dividing by a fraction, so you just multiply by the reciprocal. Reciprocal of negative 1/2 is negative 2. Negative 2 times 1, negative 2. Negative 2 equals, sorry, my headphones are messed up, equals 2 over negative 1/2 plus 1. That's equal to 0.5, which is, sorry, less than or equal to. This is equal to 4, so negative 2 less than or equal to 4. This one works, so this interval is good. Then we're going to use positive 1/2, so this time we'll get 2 or is less than or equal to 2 over 1.5 or 3/2. That's 4 over 3. 2 less than 4 over 3. This is untrue, so this one doesn't work. And then we plug in 2. We have 1/2 is less than or equal to 1 over 2 plus 1, which is 2/3. 1/2 less than or equal to 2/3. This one is true, so this one works as well. So our solution would be, oof, I'm running out of space here. Let me clear some stuff out. If you needed to write that stuff down, you can always rewind. Get rid of all this. Okay. Gives me some more space. So our answers to this would be negative 1, 0, and 1, infinity. And we know the infinity is going to be a close parentheses. Now, because this is an equal symbol, we need to figure out which one of these are actually part of the solution. This one's a little bit tough. Remember that when we ended up solving this out, we got something along the lines of, oh boy, now I need to redo this in my head. We had 1 minus x equals 0, so x was equal to 1. So that means that this value is actually a solution. We can plug that in. It doesn't give us any undefined values. Both of these, however, give us undefined values. If I plug in 0 to this equation, this is undefined. If I plug in -1, this is undefined, which means neither one of these can actually be included on our intervals. So this is going to be our final answer here. Get -1, comma 0 with closed parentheses, a bracket on the 1, and then it should be 1 to infinity. Let me double check and make sure that that is correct. Positive. Okay. Yep, cool. So sorry, I just want to double check it in the book, make sure I didn't do something wrong here. All right. So that's all for this chapter. There's a couple of other like story problem things that I'm not going to bother going over. They're long and complicated, and I'm not going to make you do any of them. So yeah, that's all we've got for this one. Again, I know this stuff is a little bit in depth, might be a little bit confusing, so try some of the practices. We'll have 2 in-person days this week, hopefully, that you guys can come in and get help if you need it. And then our test will be later in the week. So